So we continue. In this video, we do this problem. Two right cosets hx and hy are identical if and only if xy inverse belongs to h. Fundamental homomorphism theorem. So suppose you start with hx is equal to hy. Suppose hx is equal to hy. Operating both sides with y inverse. This implies hxy inverse is equal to capital H. This set of elements xy inverse operate formula. Elements this set a particular element identity E which operate xy inverse. Exy inverse. So this belongs to H. Since E belongs to H, therefore xy inverse belongs to H. So second part is proved. Now conversely, let xy inverse belongs to H. Then this implies you operate both sides with y at the right. X y inverse y belongs to hy. So this implies x belongs to hy. But we already know that x is equal to ex belongs to hx. Therefore, x belongs to hx and hy. We know that either two right cosets are disjoint or identical. Therefore, hx and hy are not disjoint. Then the only possibility is they are identical. Therefore, hx is equal to hy. Hence the solution. Now the second question. If a finite group G has exactly one subgroup H of a given order, then H is a normal subgroup of G. So given that G is a finite group and it has only one subgroup of a given order, so let the order of H is equal to K, small k, and let H is equal to H identity varanam, then H1, H2, etc. Hk minus 1. So that order of H is equal to K. Now we want to show that H is a normal subgroup of G. So for that, it is sufficient to show that G inverse, G capital H, G inverse is equal to capital H for all G belongs to capital G. Allengal GH is equal to HG for all G belongs to capital G. And in turn, this is equivalent to showing that GH G inverse is equal to capital H. G inverse on the right operate GH G inverse is equal to HG G inverse H. This is the equivalent. So, H normal and prove GH G inverse is equal to H for all G in G in the G at GH G inverse is equal to capital H in the Ganika. So first we take a particular G. We take an arbitrary G. G fix here. Now consider a G belongs to capital G and consider the set GH G inverse is equal to Aditya element GE G inverse and G. About G which H elements and right limb G G inverse which G which left limb G inverse which right to operate either the elements in a collection IDQ GH G inverse. So first element is GE G inverse, next is GH1 G inverse, GH2 G inverse, etc. GH K minus 1 G inverse. So this GH G inverse is equal to Aditya element GE G inverse or the identity. That is E GH1 G inverse, GH2 G inverse, etc. G H K minus 1 G inverse. ഇതിനകത്ത് ഏതെങ്കിലും രണ്ട് എലമെന്റ്സ് എടുക്കുക. ഇതിനകത്ത് ഏത് എലമെന്റ് എടുത്താലും say you take an x that is of the form G H1 G inverse and y is some G H2 G inverse. ഈ H1 H2 എന്നല്ല, ഏത് എലമെന്റ് എടുത്താലും അത് ഏതോ ഒരു G H1 G inverse ഒരു G H2 G inverse ആയിരിക്കും. Now x y inverse is equal to G H1 G inverse G H2 G inverse the whole inverse. This is equal to G H1 G inverse. The product in the inverse the product in the reverse order. ആദ്യം G inverse in the inverse G H2 in the inverse H2 inverse അവസാനം G യുടെ inverse G inverse. ഇവിടെ ഇത് ചെയ്യുമ്പോൾ G inverse ഉം G യും കൂടെ ചേർന്ന് ഐഡന്റിറ്റി ആവും. ഇത് so this is G H1 H2 inverse G inverse. H subgroup ആയതുകൊണ്ട് H ലെ എലമെന്റ്സ് ആയ H1 ഉം H2 ന്റെയും H1 H2 inverse എന്ന് പറയുന്ന എലമെന്റ് സബ്ഗ്രൂപ്പ് ക്യാരക്ടറൈസേഷൻ അനുസരിച്ച് this is equal to some H3 belongs to capital H. So this is equal to G H3 G inverse where H3 belongs to capital H. So this belongs to the set G H G inverse. By G H G inverse le രണ്ട് എലമെന്റ്സ് x ഉം y ഉം എടുത്താൽ x y inverse ഉം G H G inverse ൽ തന്നെ ആയിരിക്കും. Therefore by subgroup characterization G H G inverse is also a group. അതിനകത്തെ രണ്ട് ഡിഫറെന്റ് എലമെന്റ്സ് G H1 G inverse ഉം G H2 G inverse ഉം സെയിം ആവണമെങ്കിൽ two different elements different എന്ന് നമുക്ക് തോന്നുന്ന രണ്ട് എലമെന്റ്സ് സെയിം ആവണമെങ്കിൽ see this is if and only if by left cancellation and by right cancellation H1 should be equal to H2 and this is impossible. H1 H2 same alla, therefore all elements of G H G inverse are also distinct. അപ്പോൾ G H G inverse ൽ എത്ര elements ഉണ്ട്? 1 2 3 etc. k elements. Therefore order of G H G inverse is also k. Therefore G H G inverse is a subgroup of capital G of order k. But our assumption is k is the only one, has exactly one subgroup of given order. So H is the only one subgroup. G H G inverse ഒരു subgroup of order k എന്ന് കിട്ടി. അപ്പൊ പിന്നെ G H G inverse ഉം G H ഉം സെയിം ആവാനേ പറ്റും. Therefore G H G inverse is equal to capital H for G belongs to capital G. Since G is arbitrary, G H G inverse is equal to capital H for all G belongs. ഏത് G എടുത്താലും ഇത് തന്നെയാണ് അവസ്ഥ. അപ്പോഴൊക്കെയും G H G inverse എന്ന് പറയുന്ന സെറ്റ് എടുക്കുമ്പോൾ അത് ഗ്രൂപ്പ് ആണെന്ന് കിട്ടും, അതുകൊണ്ട് അത് H നോട് ഈക്വൽ ആണെന്ന് കിട്ടും. അതിനകത്ത് k എലമെന്റ്സേ ഉള്ളൂ എന്നാണ് തോന്നുന്നത്. Therefore G H G inverse is equal to H for all G belongs to G. Therefore capital H is a normal subgroup of G. Another problem, show that intersection of normal subgroups of G is again normal. G യുടെ normal subgroupകളുടെ intersection normal ആയിരിക്കും. See suppose H1 and H2 be two normal subgroups of G and capital H is equal to H1 intersection H2 to prove that capital H is normal. We need only to show that G H G inverse is equal to H for all G belongs to capital G, or in turn it suffices to show that G H G inverse belongs to capital H for all H belongs to capital H. ഇതല്ലേ G H G inverseകളുടെ കളക്ഷൻ ആണല്ലോ ഇത്. ഈ സെറ്റ് എന്ന് പറയുന്നത് G H G inverseകളുടെ കളക്ഷൻ സ്മോൾ h. ആ എലമെന്റ്സ് എല്ലാം എച്ചിലുണ്ടെന്ന് പറഞ്ഞാൽ ഈ രണ്ട് സെറ്റും സെയിം ആയി. So it's sufficient to show this. So you take an H belongs to capital H. So let H belongs to capital H. Capital H is H1 intersection H2. Therefore, H belongs to H1 and H belongs to H2. Now, H1 and H2 are normal. So since H1 is normal, G inverse belongs to capital H1 for all G belongs to capital G. Similarly, as H2 is normal, G inverse H2 element G inverse belongs to H2 for all G belongs to capital G. Therefore, G inverse belongs to H1 intersection H2, which is equal to H for all G belongs to capital G. H belongs to capital H. H element therefore, capital H is normal. Okay, thank you. E problems